Okay, welcome everybody to the INQA seminar today on 24th of September. And today's speaker is Wojtek Fedorko from the Triumf lab in British Columbia. And Wojtek will talk to us today about quantum variational autoencoders for calorimetric simulation. Over to you, Wojtek.
Thanks a lot, and thank you very much for the invitation. I hope you find this somewhat interesting for your purposes. So just a quick note about us, about Triumf. This is sort of the west side of Vancouver, UBC campus, and we are down here south of it. And yeah, that's a picture of the lab from above. And we are located on the traditional Musqueam territory, which was the First Nation that is living here from time immemorial. What is Triumf? Triumf is a Canada's particle accelerator center. We do a lot of research, education, and innovation. Our main business focuses on accelerator-based science, and that includes nuclear and particle physics, material sciences, life sciences, and accelerator physics itself. And we are Canada's gateway for big science experiments. So, for instance, experiments based at LHC, at CERN, such as Atlas, but also NA62, Alpha. We participate in big neutrino experiments in Japan, for instance, Super K, Hyper K, and a number of different experiments worldwide. And we also drive detector development for all those experiments. We do radioisotope production for medicine. If you want to have your chip irradiated and send it to space, you can do that at Triumf. We are not a huge lab. We about have 600 people. We are all over 50 years old, and we host about $1 billion of investment in scientific infrastructure. So it's fair to say that we are not a traditional research outfit in quantum computing, but we are not afraid to adopt and drive development of any technology that is useful for advancing any aspect of science that is being done here. So this is how this project has initiated, and because of the audience, I try to include different bits that might be interesting for you for sort of core quantum computing or quantum annealing researchers. So yeah, this is our accelerator complex. Is in the center here is the cyclotron driving different beams to different experiments around the site, which was hidden by those yellow blocks in this picture. Okay, the context for this project is research at the Large Hadron Collider. This is a huge accelerator based in near Geneva on the Franco-Swiss border. There are 4 major experiments, but we'll focus on those 2, Atlas and CMS, which are kind of multi-purpose experiments, and they drive a variety of different science, and they will be LHC, and those experiments are undergoing upgrades to answer some of the big questions in physical science these days. So, for instance, what is the origin of mass, which was solved by discovery of the Higgs boson, and the Nobel Prize was awarded for that. But there is a number of questions coming up. For instance, how the universe behave at its birth? Did it undergo certain types of phase transition? How will it die? Is it stable? Where did the antimatter go? What is the dark matter? And just generally question of, is there any other new physics out there? And does our standard model of particle physics square up? Or are the measurements consistent? And with these kind of science questions come really big challenges, and one of them is a computing problem. So this is a graph of the projected CPU utilization as a function of time, and around here at the end of the decade, the projected utilization of CPU rapidly increases, and this is due to basically increased beam brightness, much more data coming in. Just drawing your attention to the fact that this y-axis is in millions of CPU years annually. And this huge computing need is driven by, well, one of the major driving factor behind this need is need for simulation. So simulation at those LHC experiments is to basically do hypothesis testing. So you need to simulate nature under a variety of scenarios and then compare it to your real data to do statistical analysis to extract answers to the questions you're asking. For instance, what is the Higgs coupling, or is there a specific supersymmetric scenario out there? And so it's clear that this computing need outstrips any basically business as usual methods of doing it. And why this is so hard to do is basically, so this is a little illustration of the slice of the detector and various particle propagating. And whenever they hit this calorimetric detector, a single particle produces hundreds or thousands of secondary particles. And this is another simulation of this going on. And basically our first principle simulations need to trace each of those particles through the volume of the detector and emulate how they interact with a given volume and all the readout electronics, how they behave, etc. So you can see that for a single particle, this becomes like a huge problem at energy scales going from hundreds of GeV sometimes down to ionization energies, to electron volts. So it's amazing that it works at all, and it works great, but it's super slow. So every single shower like this takes about 1 second of CPU time to simulate. Okay, so this is the data set that we have used for this project. It is somewhat simplified, but not a lot, not very much simplified from the actual data that we get from the, let's say, Atlas detector. In fact, it was created by the Atlas collaboration, and it's an open data set. We have 100,000 electrons impinging on the calorimeter. And instead of looking at cells of the calorimeter, we're looking at some kind of voxelized small volume of the calorimeter. So we have 45 layers in this volume, 9 rings in radial direction, and 16 sort of pizza slices in azimuthal direction, comprising of about 6,500 voxels. So this is simulated in this first principle simulation in GANT4. And you can see those sort of how this behaves visually. A single shower will behave like this. You have lots of cells which are kind of empty and a lot of energy in the center, but a lot of variation as well as you're going through the detector. What is an obvious solution to this problem is to use generative models. And there is a whole industry of researchers, building more and more complex deep learning generative models to attack this problem. So the idea is that we take our real simulated data, we can spend, we can invest a good amount of time in training such a model, and basically that model usually is trying to minimize some kind of a loss between new data or synthetic data or reconstructed data and original training data. And once you have that model, the idea is that you want to have a very fast model which you can sample from, so that this model, generally speaking, takes some random input and converts it to synthetic data in the form that you need for whatever tasks you like simulating particular supersymmetric scenario or Higgs boson scenario. And this, of course, to be useful, has to be much faster than the original simulation. Okay, so why do we want to attack quantum-assisted generative AI? So the difference is that, generally speaking, in very cartoonish terms, in a classical generative AI, we usually start with a random distribution, which is very simple to sample from and very fast to sample from. For instance, a multivariate Gaussian or a multivariate uniform distribution. And then we put it through a whole long chain of also relatively simple deep learning operations, so simple tensor operations, to finally get the data that we want. And so this chain is, generally speaking, quite long and expensive to compute itself. So what we hope to do with quantum-assisted generative AI is that we would like to use our quantum processor to already generate a rich distribution to start with, and then do a simple post-processing, simple deep learning post-processing on that random data to generate the data that in the form that we want for our downstream tasks. Okay, and this whole project is based on variational autoencoder technology, let's say, or models. Basically, in those very basic implementations of variational autoencoders, you have some sort of data X that goes through your encoder. So that's takes your data and generates some kind of vector, latent vector Z, and it's parameterized by this neural network parameters phi. In a standard variational autoencoder, this encoder actually generates a vector of means and sigmas. Then you take a random number which is distributed with a multivariate standard normal distribution, and you basically shift and scale. So you multiply by generated sigma and you shift by mu to finally generate your latent space Z, and then you have a decoder which takes you back to the original, to the sort of the original representation of the data. And so this model, you can actually write down the so-called evidence lower bound. So basically log of the likelihood, called in this context evidence. You can write down the lower bound on that. And it turns out that it kind of breaks down into two terms. The log of probability of the X given Z. So this is how well you reconstruct this data. And then some kind of a regularization term, which basically tells you how far are you from a target latent distribution, how far your generated latent distribution is from some kind of target distribution. And if you impose a simple latent space, so we impose that this latent space should behave as a standard normal distribution, so a multivariate normal distribution with mean 0 and variance 1, or diagonal matrix 1, then we can write down what this should be. Basically, analytically, we can write down this so-called Kullback-Leibler divergence term. And if we assume that these variables are Gaussian, this first term, this reconstruction term, turns into a so-called mean square error loss. So it's a very simple model. This is a very simple latent space. We can analytically do the estimation of this evidence lower bound. And this reparameterization trick, which I talked about, this shift and scale trick, allows us to backpropagate the gradient from, through the model. So we can compute the gradient of this mean square error loss for a given pass forward. So, encoding and regeneration of the data, we can take the gradient back through that. Okay, so it's a very fast thing to do, of course, Gaussian sampling, and this usually is a relatively simple model. So this is very fast, but it's not very expressive. This latent space is, in fact, poor at capturing features of the data, and in practice, results are not so good, and those models kind of fell out of favor when compared to more modern generative AI. So what we are trying to do first is to sort of upgrade this this model, and instead of a normal Gaussian distribution here, we are going to put in a restricted Boltzmann machine. And this is an energy-based model, and tricks similar to original variational autoencoders were developed to basically attack this restricted Boltzmann machine prior. And so the probability of drawing a state Z is given by this energy term, so e to the minus energy of the term, normalized by the partition function. And the energy of a given state is given basically by the state of a given node with some bias and then a coupling matrix between the two sides of the machine. And so this is a much more powerful model, but unfortunately, it's also slow because sampling from the RBM is possible, but it's basically a Markov chain process. So we are kind of back at square one. I will also add that we can learn the appropriate prior. We can learn this latent distribution, which of course makes the model much more expressive. I said that this requires Markov chain sampling, and so why this is even at all practical for RBMs? It's because of the restricted nature of the RBM. So the RBM has kind of two layers. We call them left and right in our project, but sometimes they're called visible and hidden. And basically, there are connections between those two layers, but not within a given layer. And you can show that if you have, let's say, a difficult distribution to sample from a joint distribution, but somehow it's possible to sample conditional distribution, so Px given y or y given x, you can simply iterate, you sample from x given y, and then in the next iteration, you sample from y given x. And this is illustrated here on a continuous example where you have two variables and the sampling is over kind of a Gaussian distribution, but it also works for discrete variables. And the restricted part helps us here because we can simply set one side of the Boltzmann machine to some initialization, and then because the weights are going only in one direction, or from, let's say, right to left, but not within right, we can set those nodes and then sample from the left side, let's say. And then once we have the left side state, given the weights, we can sample from the right side state because each of them is just a binomial distribution in that case. So that's why we need the restricted structure to make it, at all practical. Okay, so how do we do this reparameterization trick? And by the way, this has not been invented by us. This is all described in those paper, mainly from D-Wave and collaborators early on. But basically, in analogy to this reparameterization trick, where we sample in a VAE from normal with 0, 0, and 1, we use a kind of a relaxed proxy. So we sample from a uniform 0 and 1, and then basically this Z is our binary unit. We in fact generate a logit L, which basically describes the probability of state being in a one given node being in a one state, and then we can reparameterize this expression using a Heaviside function, which goes like this basically, given the variable rho. And so this now we can, instead of having this Heaviside function, we can introduce a relaxed variable zeta, which basically replace this Heaviside function with a sigmoid function with some kind of relaxation temperature tau. And in fact, in our training, we vary this. So this describes basically how close is this sigmoid function to the Heaviside function. So we can make it arbitrarily sharp, but then of course the model becomes less trainable. Okay, so now where this doesn't need an introduction, how quantum annealing works, we have a system starting in in an initial state, which is a eigenstate of this Hamiltonian, and we introduce this so-called problem Hamiltonian in some kind of annealing schedule given by this time parameter S. So optimization is a sort of standard use case, but of course the system is in a finite temperature. So it's quite possible, and in fact, it's useful for us that the system doesn't end up always in the ground state. Instead, we have some kind of a Boltzmann distribution. So the system is free to tunnel from state to state, and when we measure, we will get this thermal Boltzmann distribution. And so this is as well quite fast to do, about 20 microseconds per sample. And samples are completely independent. So unlike in the Markov chain, where here we get one anneal equals, gives us an independent sample. So how do we then map our problem to the quantum annealer? We started with basically a fully connected RBM, a two-partite graph. We need to take into account the connectivity. So for instance, in a older architecture in Chimera, we had a bipartite structure. So all we need to take care is that we need to kind of assign the nodes to two different sides of RBM and understand what the connectivity is on a real machine. In Pegasus architecture, the more or less latest available architecture, the nodes, in fact, form a four-partite structure. So this still allows us to do block Gibbs sampling. We just have kind of a round robin, four-step round robin if we want to do classical sampling. Okay, so that's taken care of the mapping. We need to convert the RBM nodes into qubits. And it turns out it just induces simple mapping where basically the couplings in the Hamiltonian of the quantum system are given by some kind of a very simple linear transform from the RBM offsets and connection matrix. This induces a shift between the RBM Hamiltonian and the quantum annealer Hamiltonian, but it's a constant shift, so the state probabilities are not affected. So we can ignore that overall shift in the state of energy. One thing that may be interesting to this community is how we mitigate the fact that the system exists at some temperature and also can undergo freezout. So basically during training, we assume that this is our energy of the state. So basically kind of implicitly assume that KBT is equal to 1, which is of course not true because QPU is in some finite temperature. And also a thing that is described in literature is that this system can basically freeze out. So basically for large factors of the AS, the relaxation can become small in comparison to annealing time. And so the state can freeze out basically. So you may complain that this means that this is no longer in equilibrium and therefore we cannot predict what the distribution of states is. But in fact, most people assume that the distribution is still Boltzmann, and in fact, we can cross-check that, and we do get a good distribution by simply assuming that it's approximately Boltzmann distribution. And so this leads to kind of effective temperature 1 over beta. So we need to scale the couplers and offsets of qubits by this beta star. Now the problem is how to find this beta star so that we want to match the distribution generated by the quantum engineering to that generated by the classical RBM. And so this also has been described. I will maybe accelerate through it since it's a kind of a standard method. So basically, if you aim for vanishing Kullback-Leibler divergence between the distribution generated by the RBM and the quantum annealer, you can compute it, take a derivative, and sort of flip it on its head, where you basically define a redefined rescaled Hamiltonian, and this gives this kind of update rule where you iteratively update your beta star, your effective temperature in some kind of time steps. This eta is a learning rate, and what you do here is that you sample from your classical RBM. You take the mean of the energies, assuming that this is at beta equal to 1. So that's a single ensemble, single set of samples. And then you iterate, and each time you rescale your Hamiltonian implemented on the quantum annealer by this beta at a given time, and then you take a new sample set, new ensemble, you compute this average, and in the next step, you update your beta according to this rule and given some kind of learning rate. So this will converge after, tens of iterations and become stable, and then your RBM, your quantum RBM matches the distribution of the classical RBM. So another method that we have developed is that you can do this slightly differently. And basically, if you aim to equalize entropy between the distribution generated by the quantum annealer and classical RBM, you basically equate those entropies and solve for beta, and then you arrive at this equation. Again, averages of energies generated by the quantum annealer and by your classical RBM appear. You can kind of ignore this term if delta beta is small, because it basically vanishes. And so then you introduce some kind of a mapping where basically this ratio is this function of beta is given by this ratio, and you're looking for a fixed point of this function. So, fixed point is basically where you plug in an argument to a function and get back the same value. And we added this adaptive parameter beta here. So you can show that this function has a fixed point at beta equals beta QA. So in fact, we can tune this parameter delta to get faster convergence. So the stable point, fixed point is stable if the derivative of this function with respect to beta is less than 1, and you want to minimize this to get faster convergence. So basically, at any point in this kind of training of beta, you can estimate what delta you can use. So let's say I took some initial guess at beta, and let's say I assumed 5.5. I took some samples, and I can now compute this function as a function of delta, and I can see, and those fat lines correspond to different delta values. I can see that delta of about 2 is probably the more optimal one. So I assume that delta for my next update. And basically, I'm going to swim along this line. So the right-hand side axis is the ratio, this ratio of the energies. And basically, when that crosses 1, we finally got our solution for beta. And that's what we will scale our quantum RBM Hamiltonian by. Okay, so this is illustrated in this cartoon. Basically, you have this first method and this second adapted method. The RBM sample, classical RBM samples, is in the open histogram, and you can see as a function of iteration how the D-wave, energies of the samples obtained from the D-wave processor evolve as you're going through this iteration. And in fact, even though it's a bit slower in the beginning, we can get away with much fewer iterations in the end for this adaptive method. Okay, so now switching gears a little bit, and I'll just briefly mention the deep learning infrastructure, deep learning sort of broad scale architecture that in a little more detail. We have the hierarchical encoder. So basically our data together with a conditioning parameter, in our case is energy. So the energy of the particle impinging on the calorimeter is prescribed, because we want to be able to tell our model, hey, give me an electron with 2 GeV or 50 GeV or something like that, right? So this is some kind of a user input, but in the training data is some sort of a metadata. And then we have 4 layers of encoding. Each one of them embeds into different partition of the RBM and also takes the input from the previous layer. And so during the training, we pass this energy to the RBM. I'll talk how we do this in a little while. Pass the energy also to the encoder, pass the X to the encoder, but also then we pass this to the conditioning variable to the decoder. And then during training, RBM is sort of just kind of watching and tries to model the encoded latent space and tries to learn how to mimic the latent space. I should also say that we have a little feature here that allows us to model kind of on-off state of a given voxel in the calorimeter, because some of the voxel never get a hit. So this is an additional technical piece that we introduced. And during the generation, we now basically pass this energy to the RBM and then just sample from it and pass the result through the decoder. And we have kind of 2 decoders, one for the continuous variables and one for this on-off mask to finally generate our data in the form we want. And this may also be interesting to this community. How do we do this conditioning of the RBM? How do we generate the state that we want? The idea is that we don't want our quantum RBM or classical RBM to generate from any portion of the data space, let's say. We want to just generate specific examples that are conditioned on this input energy. In our initial data set, we just have one conditioning variable. This is the energy that the particle impinged on the calorimeter. But you can have more. So the way we developed is basically we fix one partition of the RBM and we do some kind of embedding. Essentially, we go from a continuous variable into a binarized variable based on how we know this behaves. So we basically take square roots, logarithms, and we generate a binarized mapping of this continuous variable, and then we replicate that mapping throughout one partition of our RBM. And the idea is that we want to force the state of this conditioning partition to correspond to what we desire during sampling. And we do this through this flux biased mechanism. So flux qubits are there to basically ensure that there's a constant ratio between the biases and the couplings in the Hamiltonian throughout the annealing schedule. And if you didn't have it, the ratio between couplings and biases in the Hamiltonian would be S-dependent, so it would depend on the annealing time. It would vary throughout the schedule. So D-Wave introduced those flux qubits to basically fix it. And so normally the strength of the flux qubit varies according to some schedule throughout the annealing process. So in a sense, we hijack this mechanism to induce very large positive or negative bias on the qubits in that one conditioning partition. And indeed, we need those effective biases to be much larger, let's say, than the sum of the couplers going into a given qubit. Anyway, so that's the mechanism that we tried, and it seems to be working. We can basically guarantee that when we sample from a QPU, this partition will have a prescribed state that corresponds to our embedding. Okay, so we check that this works. So we need to run our temperature and scaling estimation under this conditioning scenario for this to work. We also, I note, we also need to right now do tricks like waiting for the QPU to, let's say, to cool down a bit and things like this. But those are technical problems which we hope to address in the future. Our observation is that the precise value of the conditioning doesn't seem to matter. So we can run, we can run this estimation under just selected set of conditioning or even one conditioning. But it does matter that you are using those flux qubits. So in this histogram, what we basically illustrate, we take some training data and we encode them, and we basically evaluate the Hamiltonian of the RBM. Next, we sample classically, and we just plot the energy of the states, and this is given by this yellow histogram. And then we go to the QPU and again plot the energy of the states. And though if everything works, those three histograms should basically match. So this is our check that we are not very much off in terms of the distribution of samples that we're generating. And yeah, it's important to kind of follow those tricks for this to match. It's quite easy for it not to match. Okay, so the results in terms of the physics that we're generating, the particle physicists are interested in how good is the synthetic data that this model is generating. And generally speaking, at least qualitatively, we look at things like, okay, what's the energy? Like now we're talking about energy of the cells in this calorimeter. Is the distribution correct? And does it match the input data? So we here compare the input data, how our model reconstructs it, and how synthetic data looks from classical sampling and QPU sampling. We also look at things like sparsity. So for instance, the on-off state, how many cells are set to 0 in the shower, and that also seems to match. And we also do more quantitative checks now, and they also seem very promising and competitive to other deep learning models. So this here is just an example of one shower generated from this this model from the QPU. In terms of timing performance, the first principle simulation takes about 1 second per shower. With our admittedly not very optimized classical RBM sampling, running relatively long Markov chains, it takes about 2 milliseconds to generate a single shower. And QPU sampling takes us 20 microseconds, but we need to also read out the results, and actually that takes a lot of comparatively speaking, that takes the bulk of the time. We also need to do some post-processing, which about takes 60 microseconds. I should give caveats that right now we do need to implement sort of technical breaks for the QPU to program it per sample, etc. So there's definitely a lot of work to be done on sort of to address that aspect, but it seems feasible. Okay, to conclude, we know what the big challenges are in big science especially in particle physics for quite some time. So there's a big industry of people trying to address that. And in our group, we are trying to creatively explore the strengths of the Annealer to implement our quantum-assisted generative AI. This seems to be a relevant scale problem for this solution. So, we are excited that we kind of found a good match, which is a real tangible problem that needs to be solved. We are continuously improving our model, and more publications are coming out with all those things that I described before. But we already are pretty happy with how well it works. In the course of this project, we developed some new schemes for how to condition the QPU, which may be interesting in other domains, and also how to scale for effective temperature effects. We do have a bunch of technical challenges remaining, so we do hope that it's going to be solved. And then we do hope to get into more complex data sets from one of the experiments very soon. I would like to thank the team. So the project is really, Javier, the senior postdoc in the group, is really taking charge of that and working like a storm. We have a very talented set of undergrads and grads, and a number of them have been involved in this project from a variety of institutions, and we're very happy to have participation ranging from NRC, Perimeter, Virginia, and us at Triumph. So thanks a lot.
Great, thank you very much, Wojtek. Very nice presentation. Lots of interesting ideas in what is, to me at least, a new field. So are there any questions from anybody in the audience for Wojtek? Maybe I can start with a question then. Could you go back to page 24, I think it was, where you're looking at the timing metrics? Yeah. So I guess this looks great and is what you're certainly interested in this application. Can you comment on how you compare the accuracy of the simulations between your first principles case, which is presumably as accurate as you can get, and these machine learning approaches, if I can call them that, including your quantum machine learning?
Yeah, so I haven't shown those slides here, but indeed there are few ways that the community has started to do it. So they do take some kind of distances between distributions of interest, like this one, and the ones generated by GANT. So right now the let's say generative AI community or calorimetry generative AI community is not really comparing to real data. They're comparing their models to GANT. So, but indeed experiments, of course, do that. They have extensive comparisons between GANT and between parameterized fast models to real data.
What is GANT?
GANT is the first principle simulation. So okay. This is GANT here.
Yeah. Okay.
We take. So indeed, we are kind of following the same footsteps where we attempt to quantify, how good the model is with respect to this sort of standard candle of GANT simulation. By basically comparing a suite of, looking at kind of distance measures between the single variable distributions, but also things like various forms of divergence, so like Jensen-Shannon divergence between the underlying distributions as well. I would say that another thing that maybe is not done within the community is to look at kind of fine scale variations of the shower. So, there is a physical processes that's happening here. And so you can imagine that it's a conditional random process, basically, where, how much you read in earlier on, or let's say the variable describing how much energy you read out deeper on is conditioned on how much you have read out earlier on. And so there's some kind of structures here, right? And we are also trying to develop quantifiable methods of studying that, basically looking at correlations as you go deeper and deeper in the calorimeter cell. Another method was to use classifiers. So we are not currently doing that, but some people, for instance, train a classifier between your synthetic data and your first principle simulation data. But also, that's what we have done in the previous paper, when you have different types of particles, you can train classifiers trying to distinguish between particle types and check how well you can do it in first principle simulation, and then how that ports over. So for instance, can you train a classifier in first principle synthetic data and then run it on your QPU synthetic data and vice versa, and do all those kind of cross terms and check that there is no difference. The idea is that the classifier kind of learns the structures, like low-level structures inside the showers, and you can check that you can apply model learned in one setting to the other setting. So those are all different. But yeah, I think it's a very difficult thing to actually qualify, and the experiments themselves, they have their own technology, right? They have much more mature ways of doing things, but also in a sense simpler, where they basically try to parameterize the development of those showers. So you have some kind of a simple random number generator essentially, and they also study. They have a whole technology of studying how well those perform, and this does concentrate on looking at how distribution is important to particle physicists behave. So yeah, so there's many ways to skin the cat. None is perfect.
I see that Viv has her hand raised. So Viv, over to you.
Hi, nice talk and nice application. Thank you. Can I clarify whether this gets used for real-time filtering or this is saved data analysis comparisons? So, I mean, I understand reducing compute power in general, but is there also a time constraint on when you need to generate these?
I don't really think there is a very strict time constraint, but there is definitely a lot of kind of systems engineering work that would need to be accomplished for this to be useful. So right now, the sort of mainline processing is done very sequentially, where a single core will do various simulation tasks, and then perform what they call reconstruction, and that kind of philosophy would need to change, where you basically would have to offload the task of shower generation to a dedicated quantum processor, and then remerge the data stream for processing further down the line. The CMS experiment has some initial technology to do that, and I will just say that this problem is not unique to quantum processors. It's if you want to use GPUs or FPGAs to accelerate certain tasks, you run into the same problem as well. So there is work ongoing onto how we are not doing that yet in the group, but that certainly is a big task that would need to be accomplished for this to be deployed in practical sense. But so there might be some time constraints in terms of how fast you have to get the task done for this kind of pipeline to be practical, but I'm not aware of any such constraint. But this is not strictly real time.
Okay, yeah, because some of the data from at CERN, right, it's really filtered at a very early stage, so you don't save everything.
Yeah.
Good.
Yeah, so that's a different.
Yeah,
I wouldn't say that we're not filtering the data here. We're not triggering on events. We are generating completely new synthetic data samples. But yeah, it's also a huge effort to do that filtering. I'm not sure if this technique is really applicable there, except for the fact that maybe you could train it in real time on a data stream. So like in a blue sky scenario, you could imagine, okay, I'm gonna siphon off some of the data to train my model, and then throw that data away because it's just such a huge, data stream to store it. But that's, we are here in baby steps using 100,000 of events.
Wow.
And so LHC takes 40 millions of events, generates 40 million of events a second.
Yeah, I
And each
know,
one of
exactly.
them will have multiple of those showers. So
Yeah. Exactly. This is why from this slide, I couldn't tell whether you were going after the filtering or going after a later stage of the analysis.
yeah, we are targeting the generation, which comes, data is on tape already, and
Right.
we need to do statistical analysis of this data. So we need synthetic data to do that. That's where this would come in.
Cool. Understood. But thank you. It's awesome work. It's great to see this turning into something where there's some real leverage in terms of what it's capable of doing. Thank you.
Sure.
Fantastic. Well, it's 7 minutes to the hour, so I think we should probably conclude there. Thank you very much, Wojtek, for a very interesting.
Thank you.
And I look forward to seeing everyone at the next INQA seminar next Tuesday. Thank you. Bye-bye.
Bye.